So anytime that we talk about breaking an amino acid down, glutamate dehydrogenase is a key component of all of this. GluDH is a key component because what it does is ultimately it's an enzyme that's going to remove ammonia or ammonium by a process known as oxidative deamination. So anytime you see that oxidative, whenever I think of oxidative, I want you to, or when you think about oxidative, I want you to think of redox. And whenever you think of redox or an enzyme, an oxidation reduction reaction catalyzed by an enzyme, I want you to think about either NAD plus or NADP plus. I want you to then think about NADH or NADPH. So you have this oxidation reduction taking place, but what we also have is a deamination or a removal of an amine. Now in this case, we have glutamate plus NADPH or NADP plus. That's going to yield alpha ketoglutarate, an ammonium ion, and NADPH. So our positively charged molecule will become slightly less positive. It's going to go from positive to nothing, which is an example of reduction. Therefore, glutamate is going to become oxidized as it goes to alpha ketoglutarate. Okay, now a little bit more about our enzyme that we're going to be discussing and dissecting here. Glutamate dehydrogenase. Glutamate dehydrogenase is a reversible reaction. This is a reversible reaction that has a very high Km for glutamate, which means, in other words, low affinity for GLU. Now, what this reaction looks like is this right here. Glutamate is going to be reduced first to aminoglutarate. That aminoglutarate is then going to have that NH2 simply hydrolyzed away. So we're going to end up with alpha ketoglutarate. So if you notice here in this first step, glutarate, what we're doing, or glutamate to go to the alpha aminoglutarate is we're losing this hydrogen, and then we're losing another one right here, so that we end up with a double bonded nitrogen with two hydrogens on it, making it NH4 plus, or NH2 plus, I'm sorry. Now, ammonium, don't get it mixed up. Like, this is the most important part of all of this reaction. That NH4 plus that we've generated through the oxidative deamination of glutamate is toxic. It can lead to, kind of on a simplistic level, can make you tired. You'll kind of be lethargic, but if you have too much ammonium in your system, that lethargy is going to kind of persist. It's not like, oh, I need to take a nap for an hour. Instead, it's going to be like almost a depression level of lethargy. Like you can't really move, you can't get out of bed. In addition to that, in developmental levels or in developmental phases, an increased ammonium concentration can lead to some cognitive delays. When your body is functioning properly, what you're going to be able to do is you're simply going to excrete NH4. Fish are going to excrete NH4 simply in its basic state of, it's going to excrete NH4 as NH4 plus. Mammals, on the other hand, what they're going to do is we're going to go about making a molecule known as urea. Urea is the way that we're going to take NH4 and process it, package it a little bit differently so that we can get rid of it. And we're talking about a molecule that looks like this. So there's urea. We can basically process two ammoniums at a time whenever we're getting rid of urea. Birds and reptiles, what they're going to do is they're going to take any excess ammonia or ammonium, I'm sorry, and they're going to package it into a molecule known as uric acid. And those uric acid crystals are going to be um, birds and reptiles are simply going to um, package up those uric crystals or uric acid crystals and excrete those. Mammals don't have that opportunity, nor do fish. So mammals have to take this ammonia and package it and make urea. The way that that's going to be done is this process known as the urea cycle. It's all here, and it's definitely a lot to swallow here. But we're going to kind of break it down and work through the different components, and kind of talk about where these different things are going to take place. So I'll be bouncing back and forth between those two cycles. This is another rendering of it. And notice how the urea cycle kind of runs side by side with the citric acid cycle. One thing that makes the urea cycle kind of interesting is that the urea cycle functions in the cytosol as well as in the mitochondria. So there are components of the urea cycle that have to enter the mitochondria in order to be metabolized. Now, with that said, I really like this model right here because I think it simplifies it quite a bit, especially if you focus simply on the urea cycle. We have ornithine. Ornithine gets transported into the mitochondria. Ornithine with a molecule known as carbamoyl phosphate will make citrulline. Citrulline is going to be transported out of the mitochondria. With aspartate, citrulline will make arginosuccinate. Arginosuccinate will be broken into arginine and fumarate. Fumarate is a molecule that should sound a little bit familiar to you because we've talked about fumarate in the citric acid cycle. Well, fumarate can be metabolized to malate. Malate, use a malate aspartate shuttle to get back into the mitochondria, in which case it can go about being utilized in the citric acid cycle. Now, if we go back home to the cytosol within the urea cycle, well, that arginosuccinate, the half that did not get broken into fumarate, is going to be made into arginine. That arginine is where we are going to release our urea. We're also going to release our ornithine, which can bring us back to being transported back into mitochondria and so on. Because at this point in time, we don't really care too much about the specifics of the citric acid cycle. I mean, it's relevant and important, but we've already kind of talked about that. So this slide, I think it really captures this, what could be the simplicity of it and the interconnection between the urea cycle and the citric acid cycle. With that in mind, here are the enzymes of the urea cycle. The enzyme carbamoyl phosphate is an enzyme that utilizes 2 ATP, HCO3, and NH3 to make carbamoyl phosphate, 2 ADP, and 2 inorganic phosphates. Another molecule, ornithine transcarbamylase, is going to take carbamoyl phosphate, carbamoyl phosphate and ornithine to make citrulline. Arginosuccinate synthase will take citrulline and aspartate to make arginosuccinate. Arginosuccinase will take arginosuccinate to make arginine plus fumarate. Arginase will take arginine to release urea and ornithine. Okay, so if we go back a little bit, let's try to figure out one of these components using this model right here. Ornithine, where we started, and I'm going to go ahead and erase all my markings on this slide. Ornithine being transported into the mitochondria. Okay, ornithine being moved into the mitochondria. Well, we're more than likely not going to be using an enzyme for this so much as we use a transporter molecule. So that's not listed there, but first time that we see ornithine, it's actually in the mitochondrial matrix. It's in the mitochondria. So ornithine plus carbamoyl phosphate will lead to the formation of citrulline. So if I jump back, we have ornithine plus carbonyl phosphate to yield citrulline. I'm going to label this 1. That citrulline will then be used in combination with our amino acid aspartate to make arginosuccinate. Let's go back, or sorry, let's go back. So this step right here is 1. The next thing that we've got to do is we've got to move our citrulline out of the mitochondria. Once that's out of the mitochondria and into the cytosol, that's where we have enzyme number 2 that combines citrulline and aspartate into making arginosuccinate. That arginosuccinate is going to be broken into arginine and fumarate. Arginosuccinase is going to move arginosuccinate into arginine plus fumarate. This would be step 3. Step 4 is going to take arginine, split off our urea into, or sorry, take our arginine and make urea and ornithine. So arginase is going to do that. And that's kind of everything there. Now, with that in mind, let's go look at this. 1, 2, 3, 4. The 4 biggest steps of the urea cycle. Of the 5 enzymes that were listed, there was one that we didn't talk about, and that enzyme was making carbonyl phosphate. So I'm going to label this as our step 5 enzyme. But let's go ahead and jump back to this more complicated model. Now, this more complicated model, I'm going to have our numbering be a little bit different, because what it's going to do is it's going to start out with ATP, HCO3, and H3 to make this molecule right here, a carbonyl phosphate. That carbonyl phosphate will be combined with ornithine to make citrulline. So they have that labeled as 1. And then second is going to be formation of citrulline. Citrulline has to be transported out of the mitochondria into the cytosol. That citrulline will pair up with aspartate to make arginosuccinate. That arginosuccinate will be split into fumarate and arginine, and that arginine, which is right here, and actually I'm going to go ahead and erase that and focus in specifically on the R group. You know, one of the things I think whenever it's time for me to learn my amino acids, arginine was the functional group that I struggled with the most. And I think the reason for that was because you have this R group that is H2, 3. I just have to draw the whole amino acid now. And H, C, and H2. H2 and that would be positively charged. Now, this is an amino acid that I always kind of struggled with, in part because you have this R group that's kind of funky. It's got a hydrocarbon chain and then NCNN. And I would always screw up where I would just be like, I don't really want to draw this nitrogen right here, because I just would forget to. This whole N, though, is what is ultimately released. It's released as urea, where urea is H2N, C, H2. That urea is released, giving us everything that remains. And in which case that's going to end up as NH3 plus, and that is the amino acid known as ornithine. Ornithine is an amino acid, but what's important about it is it is a non-proteinogenic amino acid. Okay, so ornithine can be transported back into the mitochondria, where it is then combined with carbonyl phosphate to make citrulline. Citrulline plus aspartate yields arginosuccinate. Arginosuccinase is going to give us arginine and fumarate. That fumarate can then be metabolized into malate. Malate dehydrogenase can take malate to produce oxaloacetate. Oxaloacetate can go on to be used for gluconeogenesis because oxaloacetate is a citric acid cycle intermediate. So it could find its way in the citric acid cycle. It could also find its way into a number of different pathways, especially considering the connection that we just made with our lipids and the citric acid cycle. So what I want you to take away from all of this right here is I want you to start out with this. Okay, that's a lot of this structure, a lot of this model. But then narrow it down and say, what is this molecule? Ornithine. Where is it? It's in the cytosol. It has to get into the mitochondria. Why? So that I can make citrulline. Citrulline, much like ornithine, is an amino acid. NH3, CO minus. Is it a proteinogenic amino acid? No, it's not. Citrulline is then transported out of the mitochondria. So we have this movement of molecules, and the entire purpose of this cycle is to generate this right here so that we can ingest proteins, break them down, and they do not, and we can extract energy from them, and they will not destroy our brains. That's effectively the point. So the urea cycle is something that we have to have working so that we can ingest proteins, process them. After something has made its way to lysosomal degradation or degradation by the proteasome, what is going to happen? Now, the thing that we didn't really talk about a lot was right up here. That's our enzyme glutamate dehydrogenase. Glutamate dehydrogenase is an enzyme that will lead to NH3 being produced in the mitochondria so that it can then be used for making carbonyl phosphate. All right, well, those are all of your enzymes.